Welcome back. In this section, we're going to be looking at some applied minimization and maximization problems. For these problems, we're going to have some sort of a story, and here's some general guidelines for dealing with that. Firstly, we're going to think about what do we know, what do we not know. So, thinking about the quantities in the story, and more than likely making some sort of a diagram or a sketch. So, for this, if it's something geometric, it would make sense to have a little sketch given or a diagram given. And then once I've done that, once I've sort of settled into what variables do I have and what do I know and what do I not know, I'll construct my first equation. This is the objective equation. This is the thing that I'm hoping to minimize or maximize. This may or may not be in terms of only one variable, and unfortunately, this is calculus of one variable that we're currently learning. So, to maximize an objective equation, it really needs to be an objective function of one single variable. That's where these secondary equations are going to come in handy. We're going to use these constraints, these other equations that come from our story, so that we can rewrite our objective equation as a function of one variable. And then once we've done that, we can go ahead and minimize or maximize using our first or second derivative tests to help us out, and what we know about continuity and differentiability and extrema and all the rest. One thing that I'm going to just make a note of is here at the very end, I mentioned to make sure that you take note of the domain of your objective function. So once we've rewritten our objective equation so that it's a function of one variable, we also want to think about what the domain is, because of course, as you're remembering from the extrema sections from earlier, the domain is very important when we're thinking about where is the maximum or where is the minimum. In particular, we're going to be looking for absolute extrema here. So if we have a closed interval for our domain, then we're going to need to check what's going on at the endpoints. Even if we have an open interval for our domain, we'll still need to check, except we'll use limits to figure out what's going on near the endpoints, because we want to find the largest or the smallest value of whatever it is that we're looking at. So for the first story that I've gone here, I've got a farmer is making a bunch of plots of land, two little rectangular plots, sharing a common side, and they've got 300 meters of fence to do so. So I'm just going to do a little doodle here of these two little plots. So those are my two plots sharing a common side. So if I wanted to just start labeling things with variables, I could say I'll have the x's being the common sides and the y's being the horizontal sides, or whatever a disposition of variables and letters you feel like choosing. I'm using x's and y's here. Maybe you could choose a's and b's or whatever you feel like choosing. Or lengths and widths even. So how about I do that? I'll go for lengths and widths. There we go. And so if I'm looking for this, I want the dimensions of these two plots that will have the maximum area. So for the area of the whole thing, the area of the two plots together, that would be 2 times length times width. Each rectangle has an area of length times width, and the total area is twice that. Of course, right now I can't maximize area because this is not in terms of just one single variable. This is in terms of two variables. So now I'm going to have to think about what else have I not used yet. And it's this fact that we have a total amount of fence of 300 meters. So that means that if we added up all the lengths and added up all the widths altogether, that should add up to 300. So in other words, as a second equation, we know that 4 width plus 3 lengths adds up to 300. So now what I'm going to do is I'm going to take my constraint that I have here and use that to rewrite my objective equation, my objective function area, in terms of just one single variable. So what I'm going to do now is I'm going to rewrite this, bringing the L to the other side. and then dividing by W, or dividing by 4 rather, to get W is 75 minus 3/4 length. Right now, this is going to take a little moment here to think about what this is telling us. So if you're thinking about the values that you could have for length now, we know that for sure length couldn't be any smaller than 0, because of course then it's not a length. And in fact, I would say for this the length couldn't be 0 either, because if it was, you wouldn't really have rectangles anymore. You would just have a bunch of widths, and that would be that. So I would say that the length needs to be larger than 0, but I can also find out what the maximum value for my length is here. If my length were anything above 100 or 100 or larger, then that would make my width negative, and of course that's not possible. I can find that if I have 300 as my maximum amount of fencing, then the biggest amount I could have for each L is 300. Is 100. And again, I couldn't have my length being exactly 100, because if I had 100, 100, 100, then I'd have no fencing left for my widths and I wouldn't have any rectangles. So that means for my length, it's somewhere between 0 and 100. If I were to take that formula for width and substitute it into my area equation, I would now have an area function just in terms of one single variable. Instead of area is 2 times length times width, its area is 2L times 75 minus 3/4 L. Or in other words, this is now area as a function of length. And in fact, I can probably just expand that now. Multiplying on ends, that would give me 150 times L minus 3/2 L squared. Okay. And when we thought about where L is, that's us thinking about the domain of my area function. So for my area function, although this is a polynomial, technically you could put in whatever value for L that you'd like. It is limited to between 0 and 100 for this story. Okay, so I guess we're going to have to do a little bit of calculus now. Let's figure out, where do we have any maximum or minimum values. I know that a maximum or a minimum could happen at a relative extremum, so let's take a look at our derivatives and see what we get. So firstly, if I were doing my derivative, a prime of L, I would say, well, we've got minus 3/2 L squared. When I take the derivative of that, it's minus 3/2 times 2, or minus 3 L to the 1. And then I also had 150 L. Derivative of that is 150. There's no places where my derivative is undefined. So when I'm looking for critical numbers, it's only places where my derivative is equal to 0. And there's only one value for that. When I solve for where is my derivative equal to 0, I find that it only happens to be at 50. Okay, so let's figure out for that critical number of 50, is that a relative minimum, relative maximum? What's the story there? So let's use our second derivative test for that. Second derivative would be just -3. And there's no place to put in a value for L, so no matter what L is, the second derivative is always -3. In other words, we are always concave down. So in other words, we have a relative maximum at at length equals 50. And if we wanted to find out what that relative maximum value is, we could find out and say, well, using our area formula, our area at L equals 50 is 150 times 50 minus 3/2 times 50 squared. So we can come up with our total area for this, and that is 3,750 50 square meters. So those are the two plots together. Right now, I've only confirmed that it's a relative maximum. I need to confirm whether that's actually an absolute maximum. Right now, I know that I've got a relative max when L is 50, but I want to also know what's happening at the endpoints. Because if by some twist of fate we had a graph for A of L that where maybe we had a peak at 50, but maybe it's even higher at 100 and it's not a relative extremum, maybe then the 50 is not a absolute extremum after all. So same thing could possibly be happening on the other side of things. Maybe the y value when we're getting close to 0 is much higher than the y value at 50. So that's what we need to figure out. What's going on at our endpoints? Then we'll be able to confirm whether this relative max is actually relative or relative and also absolute. So I guess on my next page, I'm going to do a little bit of looking at that. If I were looking back to my first page, though, I'm going to remind myself that my domain is an open interval from 0 to 100, not including the 0, not including the 100. So I'm not going to calculate what is A of 0 and what is A of 100. Instead, I'm going to look at what happens with limits, because our domain doesn't include 0 or 100. So really, if I wanted to look at what's happening to my area function at these endpoints, I would have to do it via limits. So if I were looking at what happens as we're getting close to 0, number one, of course, we're getting to 0 only from the right-hand side. So that means I'd be looking at a right-handed limit. So what happens as L approaches 0 from the right for my area function? So if you were to look at our area function, which was that 150L minus 3 halves L squared, you'd find that as L goes to 0, this whole thing goes to 0. Which kind of not a surprise. If we had no length, then we'd have no area. And same sort of thing is happening if the length was the extreme. We had the largest that our length could be was 100, and in fact it couldn't even be 100. We could just get close to 100. So in other words, we'd be looking at what happens if we're approaching 100 from slightly smaller values for our area function. And if we're looking at our length being just a little bit under 100, getting close to 100 from the left, you'll also find that it goes to 0 as well. So it turns out that our maximum at 50 is the absolute maximum. So the absolute maximum area of the two fields is 3,750 meters squared. And we wanted to know what were the dimensions. The dimensions of each field was length is 50, and then the width is, and to find that, of course, we need to go back to our original. We had our constraint where we related width and length. So if we know that if we know that length is 50, we can use that equation to find out what width is, and it turns out that width is 37.5. And of course, the units for both are meters. So if we have the shared side being 50 meters and the widths are 37.5 meters, that will give us the maximum area for the two fields. Okay, another little geometry kind of a problem. I've got a piece of metal. It's a square piece of metal, 18 centimeters on each side. And then from each of the four corners, I cut out a square with a side length of X centimeters. So I guess what I'm going to do first is start drawing things. So here's our basic square piece of metal that we had. And originally that's 18 centimeters by 18 centimeters. And then we say in the story that what we're going to do is at each of the four corners, I'm going to cut out a little square with a side length of x centimeters. So I will snip out a little x by x square, and that way I'll have a little sort of a flap there. And I'm going to do the same thing on all four corners. And each is going to be the same size of a little square that gets cut out, which is x by x. So that now I'll have this sort of shape, a sort of a plus kind of a shape with my metal. And then what I'm going to do is take these four little flaps and then fold them upwards. So I've got now sort of a square base with four flaps, and I'll be able to fold them upwards so that I'll have a little base and four sides. So I'll have a nice little open box. So first we need to figure out some things about sizes. If the whole thing across was 18 centimeters and I've taken away an x and another x, then the actual distance that's left behind is really 18 minus 2x. And I can say the same thing about for the vertical side of things. Again, it was 18 centimeters for the whole side, and we've taken out an x and another x. In other words, we've taken out 2x. So again, we've got 18 minus 2x. So that means that if we're thinking about what we get when we fold up our four flaps, we get an open box where you have 18 minus 2x for the length and the width of the base. And each of these flaps, that's the height of the box. So that means what we've really got for this box is something with a square base with a height of x. And we want to know what are the dimensions of the box where we get a maximum volume. So already I can go ahead and create an equation for this, so that's not too bad. So as far as the volume goes, I can say, well, volume is length times width times height, which is x times 18 minus 2x squared. So again, we're going to think about domains here for just a minute and think about what sort of restrictions we have on x, which is how much we can cut out. So firstly, the smallest we can cut out would be to cut out nothing. And of course, if we cut out nothing, if x was exactly 0, then we wouldn't have a box because we'd have nothing to fold up. So when I think about my domain, I'm not going to say that x can be as small as 0. So it'll be 0 rather with round brackets, because I can be close to 0, but I won't be ever exactly 0. And if we're thinking about the maximum that I can cut, the side lengths were 18. So if you cut 9 centimeters on each side from each corner, you've basically cut out everything. So 9 would be the biggest amount that you'd cut. And again, if you cut exactly 9 centimeters, if I took an 18 centimeter squared and cut a 9 by 9 square out of all four corners, I've cut out everything and I no longer have any metal left and there's nothing to fold up and make a box with. So for the 9 as well, I'm going to say that that's a round bracket. We can cut close to 9 centimeters off, but not exactly 9 centimeters, not if we'll want a box. So I'm going to, and I just noticed my lack of a square there, sorry about that. I'm going to now think about finding the extreme values for this function. So first things first, I know that at the very end of it all, I'm going to have to do the same thing that I did with the last problem. I'm going to have to investigate what happens as we approach 0 from the right, what happens as we approach 9 from the left, and also what happens at any of the relative extrema that we get for v of x. And then I'll be able to piece together what do we have for our absolute value. What is the maximum volume that I can get for this box. So if you're looking at our volume function as it currently stands, which is x times 18 minus 2x squared, we didn't need any sort of a constraint function. We already have this as a function of x, so we're good to go. You might feel tempted to expand this, to turn this into a big polynomial. You can resist that urge because, of course, we have product rules, so why bother wasting our time doing that kind of algebra when I can just use the product rule? And so that's what I'll do. I'll take the derivative with product rule. First thing as it is, derivative of the second, and derivative of the inside, there we go, plus the second thing as it is, and derivative of the first. And the derivative of x is just 1. So here I can see that I've got 18 minus 2x's that I can take out of both terms. And that leaves x times 2 times negative 2. So I have a minus 4x left in the first term. And I have a single 18 minus 2x left in the second term. Or in other words, I have 18 minus 2x times 18 minus 6x. And I'm going to let v prime be equal to 0. And for that, of course, I already have it nicely factored, so that one's easy to say what my critical numbers are. I have two possibilities. One of them is from 18 minus 2x equals 0, which turns out to be 9. And then the other one comes from 18 minus 6x equals 0, and that turns out to be 3. As far as the 9 goes, I can just skip this. This is not inside my interval of 0 to 9. I said that my interval was from 0 to 9 round brackets, not including the 0, not including the 9. So that critical number, that's out of my discussion area, so I can just sort of skip that. Of course, I'm still going to talk about what happens as we get close to 9 when I look at the limits at the endpoints. But as far as critical numbers go to investigate, I have 3. That's the only one to investigate. So I guess now the next thing for us to do is think about what's going on at 3. Is that a minimum? Is it a maximum? So on the next slide, let's continue on by finding our second derivative. Second derivative test, easy enough to do. I'm just going to use product rule as it is. So first thing as it is, derivative of the second, which is minus 6, plus the second thing as it is, times derivative of the first, which is minus 2. And then if I were to expand this and then clean it up, I get negative 144 plus 24x. And if we wanted to look at what happens, what's our concavity like at 3 at our critical number, it turns out to be plus 24 times 3 gives me negative 72. So it looks like we are concave down. That means we have a relative maximum at x equals 3. And if we wanted to go backwards, we could find out what that relative maximum volume is. So if we went back to our original equation and put in 18 minus 2 times 3 squared, we'd find that our maximum volume turns out to be, or our relative maximum volume turns out to be 432 centimeters cubed. The question is this the absolute maximum? So we only had one relative extremum that we've had in our interval. That was this relative max at 3. The question is what's happening as we're getting close to 0 and what's happening as we're getting close to 9. So here's where we need to look at our endpoints. What happens to our volume function as we're getting close to 0 from the right? And for that one, probably not surprisingly, if you didn't cut anything off of your metal square, then you're not going to have any volume at all. And as x goes to 0 from the right, our volume function goes to 0. And same thing with the other extreme endpoint, which was 9. If we approach 9 from the left for our volume function, we'll see that again, you're going to wind up with something that's approaching 0. So for all the values that we found, 432 was the largest of the three, so we definitely do achieve the absolute maximum volume of 432 centimeters. So the dimensions of the box is height is 3 centimeters, and that the base is 12 centimeters by 12 centimeters, and that this gives the maximum volume of 432 centimeters cubed. So for the problem that we have, there is indeed a maximum, and the maximum happens to be achieved when x is 3, when we cut 3 centimeters squared little squares out of each corner of our original sheet of metal.